Hey everyone, so here we're going to talk about problem number 3 in this equilibrium homework set. So here this problem states that the type of rope used to support the crate in the figure below can withstand a maximum tension of 1500 newtons before it breaks. What is the heaviest crate the ropes can support? Right, so basically we're trying to figure out the mass at which this block here can have before either this rope, or even this rope here is going to break. Right? So for the sake of time, I'm basically going to talk through the solution I've posted to hopefully kind of explain the thought process here a little bit more detail than just reading through the solution. Right, so I've first thing I did was redraw the diagram, right? So I've got my block here with two ropes going off at angles where we know that the angle with the ceiling or whatever the structure is 30 degrees for this rope and 45 degrees with that rope. So if I'm drawing a free body diagram, I'm analyzing this point right here, right, just for simplicity's sake, right, where we know that the force acting down here, right, we could call that a tension because it's a rope, but I'm just going to label it as weight because it is going to be equal to the weight of the block. Right, which we know is going to be m times g. And then I'm going to label this left rope here tension 1 and this right rope here tension 2. Right? And I know here that all these vectors here are not perpendicular with each other, so I really apologize for the background music, but I'm kind of recording this while other classes are going on. I apologize if you can hear that. Nonetheless, that these vectors here are not perpendicular. All perpendicular to each other. They're not what's actually called orthonormal, but nonetheless, I'm going to define my coordinate system just to be upwards as positive y and rightwards as positive x. So then based on my vectors here, I'm going to have to modify my diagram so that my tension forces I can break them up into their x and y components. So if I do that, my tension 1, right, well that's acting left and upwards, right, so I have my x component acting to left, my y component acting straight up. Similarly for tension 2, that's acting rightward and upward. So my horizontal piece is T2x since that's in my x direction, and T2y is straight up since that's in my y direction. Right, so kind of my modified diagram is this, right, and since we're in equilibrium, right, we know from this diagram that my horizontal vectors, they're going to have to cancel out because the acceleration of this system is 0. So I know my x component of T1 and my x component of T2 will be equal to each other. Right? This here doesn't really help us much, at least for the time being, when we're first kind of looking at this problem, right? Because we want to figure out what the mass of the block is, where T1x and T2x don't involve this mass, right? So it's going to make more sense to kind of start vertically because we know that the weight here is going to equal to T1y plus T2y, since again, we're in equilibrium, so there's no acceleration, so our vertical forces will also have to cancel out, right? So kind of saying this a little bit more rigorously, right, we know the sum of the forces in the y direction is equal to 0. So what we have going on in our y direction are two positive tension component forces and a negative weight. So you can write that as force of gravity if you want instead of W. I just use W here. We know that's going to sum to 0, right? So then I'm going to draw my trig triangles here, my right triangles, to figure out the expression for these component vectors of tension. Right? So based on my triangle, so looking at T1, I know T1 was acting this way with an angle here of 30 degrees. Right? So when I break those up into these vectors, I see my T1y is opposite of my angle, so I know I'm going to use the sine function. Right? So T1y, based on our trig triangle, is T1 sine theta. T2y, similarly, is T2 sine theta, right? For the same reason, just different trig triangle. Excuse me, not theta, phi. So I'm using a different Greek letter here because our angle is different. Right? You can label this theta 1, theta 2 if that makes you more comfortable. I'm just using another Greek letter here that's often used for angle. Right? So my 30-degree angle is going to be theta, my 45-degree angle is going to be phi. And then I also here just wrote down the x components. Right now this is not necessary, but later on this problem we will see it will be, right? So I recommend if you're solving through this problem, right, initially maybe you won't actually write down those components because you may not need it, right? It may not be obvious to you that we need it yet, and that's okay, right? But we know we need to then, rewrite T1y and T2y in terms of those tension forces and their subsequent angles with the trig functions, all right? Now, looking at this equation, right, we do not know either of those tension values. We know those angles, and I guess technically speaking, we don't know the weight either, right? We know it's going to be equal to mg, but we don't know anything further. But we do know that the maximum tension value that we can have, was it 1,400 newtons if my memory serves me right? Let me go back to the problem. 1,500 newtons, right? So that's going to be a known quantity we have. And that will be the value of one of these tension forces, depending on how we solve the problem, right? Because that's the maximum value it's going to have before it breaks, right? So even though there's 3 unknowns here, really we only have 2, since we know that one of those tension values is going to be 1,500 newtons, while the other one's going to be less. So essentially here, we need another equation, right? We can't solve an equation with 2 unknowns with one equation. So, very similar to other problems, we're going to use it, look at the other direction to find our other equation. Right, so here we can sum their forces horizontally, and summing horizontally we see that T2x is equal to T1x. Right, so I'm looking at this equation here. So writing this in terms of our tension forces and their subsequent trig functions, we get T1 cosine theta is equal to T2 cosine phi. So again, looking at this here, we have our 2 tensions being unknown quantities, where one of those eventually will be a known quantity, but nonetheless, we have we have our system of equations, long story short, since we know these angles. So we're going to be looking at these 2 equations here we found. Right? So what I did was I solved for one of these tension values, so I just picked one. So let me scroll. Right. So I decided I am going to solve equation 2 for value of T1. Right, so rearranging equation 2, we get this expression here. Right. And I'm going to take that T1 and plug it into my first equation. Right. So I do that and simplify. We get this expression here, right? So remembering that sine theta over cosine theta reduces to tangent of theta. So we have the expression that our tension multiplied by all this trig stuff is equal to the weight. And we know that our tension can have a max value of 1,500 newtons. So I'm going to plug in 1,500 newtons here and see what our weight ends up being. Right? So 1,500 newtons, and I plug in my angles to my trig functions, and I get that the weight is 1,673 newtons. All right, cool. We could solve for mass from here, but we don't know if this is actually our answer, right? Because we need to look at the case at would be if what happens if T1 instead was 1,500 newtons instead of T2. So this time I solved for using equation 2. I solved for T2 instead and then plugged it into equation 1. Right? And when I did that, let's scroll down a bit. Right? So when I did that, I got an expression here, somewhat similar looking, right? Because we do have some symmetry going on here, not exactly the same. So we have tension 1 is this multiplied by all this trig stuff again. So let's test out what happens when T1's 1,500 newtons. So we plug in 1,500 newtons for T1, whatever angles we have corresponding to our known quantities, and we end up seeing that when T1's 1,500 newtons, the weight is going to be just above 2,000 newtons. So we see here that it is easier to break rope 2, right, or tension 2, right? It takes less weight in order to cause it to break, right? So we can see that because 1,600 is less than 2,000, right? So then going back and looking at our value of 1,600 newtons, approximately so, right, we know that our weight's just equal to mg, so I can solve for mass by taking this weight divided by acceleration due to gravity, and we get 167 kilograms. Which actually, that's probably too significant of figures, right, because we've got 2 sig figs in this problem. So then our answer should actually be 170 kilograms. I apologize for that. All right, so hopefully that was helpful in me kind of explaining through this process. This is a pretty involved problem, a nice stretch, so to speak. Hopefully it was fun. I can see where it could be frustrating, but I think it's a fun problem. Anyway, have a good one.